So if I gave you something like f of x equals the natural log of x over x minus 1. We know that the function would not exist at 1, right? Because that makes the denominator 0. But if I were concerned with the limit, we would still need a way to evaluate the limit there. And we know we've done all these kinds of tricks for evaluating the limits, you know, factoring, reducing, multiplying by conjugates, all those types of things, to get it to the point where we could just plug in the number. But we can't just go straight to our limit laws. In general, if we looked at this one, the natural log of 1 is 0, and 1 minus 1 is 0, so this is actually 0 over 0, if we were just to plug it in. So that's what's considered an indeterminate form. You can't just look at that and know what it means. So that's all that's telling us. If you have 0 on top and bottom, that is an indeterminate. We have worked on some of those before by factoring and reducing, but in this case, would you be able to factor the natural log of x and cancel anything out? No, so that's not an option here. So in that scenario, we can use L'Hopital's rule. L'Hopital's rule says if you have the numerator and denominator are both differentiable and g prime, so the derivative of the bottom, is not 0, then we can evaluate the limit by doing the derivatives of the top and bottom separately and evaluating the limit of that piece. Now this only works if it is of a specific type. If it's 0 over 0 or infinity over infinity, then we can try this trick. It can be like negative infinity over positive infinity, that's okay, or negative infinity over negative infinity, that's okay. But if you have a 0 over 0 or an infinity over infinity, in those scenarios we can do L'Hopital's rule. So we will do the derivative of the top, the derivative of the bottom. So not even a full quotient rule, we're doing the two separately, and then evaluating that one. So L'Hopital's rule, it is something that we can do more than once. So we can, you know, if we do it one time and it's still 0 over 0, we can do it again. So we are going to use that to evaluate this piece. Right now, when we look at it, the natural log of 1 is 0. It's like saying e to what power equals 1. So a log of any, no matter what the base. If it's log of 1, it'll be 0. And that's 1 minus 1 is 0. So this is 0 over 0, so we can do L'Hopital's. What I usually do to denote that I'm doing L'Hopital's is I put an LH over my equal sign. And I would appreciate you doing that when you're working the problems, just so I know where you are applying it. So then my limit stays. What is the derivative of the natural log? That's the exponential form. 1 over x. The derivative of the natural log is 1 over x. We did that right before Christmas. On the bottom, what's the derivative of x minus 1? 1. Okay, so this is just the limit as x approaches 1 of 1 over x. Can you plug in a 1 there? Yeah, 1 over 1 is 1. So we simplified it to a point that we could reduce. Any questions? Okay, so we're just going to look at some more limits. The limit as x approaches infinity of e to the x over x squared. So if we just plugged in e to the infinity power, what would that be going towards? infinity. Infinity squared is going towards infinity. So this is infinity over infinity, which is an indeterminate form. So we can do L'Hopital's. Derivative of e to the x is derivative of x squared. Okay. At this point, e to the infinity is going to 2 times f, or 2 times infinity is going towards. So what do I need to do? Do it again. So if you do it multiple times, just make sure you're labeling each time. Okay, e to the x, the derivative of that is still e to the x. Derivative of 2x is 2. So now the top, e to the x, is going to over 2, which is still infinity. But I no longer had an indeterminate form because it was infinity over a number. So that's why we're able to just evaluate it.
So we just keep doing it until we get like a 0 thing?
Mm-hmm. As long as it's still 0 over 0, or infinity over infinity. Let's try that. This is the natural log of infinity. The graph of a logarithm looks like this. We have a vertical asymptote at 0, and then it's just rising. So, natural log of infinity, it's going towards infinity. It's going to keep rising. The cube root of infinity, still infinity. Alright, so we have to do L'Hopital's. You might want to rewrite this. The cube root of x, if you need to, you can write that as an x to the 1/3, if that's helpful. So then we can do our L'Hopital's. The derivative of natural log is, okay, derivative of x to the 1/3. 1/3 x to the, we have 2/3. Oops, what did I fail to write on that stuff? Yeah, don't forget your limit. Okay, I'm going to clean this up a bit. A -2/3 would put that on the bottom. So to divide fractions, we flip and multiply. So I've got my 3. Do we have more x's on top or bottom? What's bigger, 1 or 2/3? 1. So we have more x's on the bottom, it'll end on the bottom. 1 minus 2/3 is 1/3. So that whole thing simplifies into 3 over x to the 1/3. If I plug in infinity, 3 is just going to go to 3. Infinity to the 1/3 is going to infinity. What's 3 over infinity going to? 0. And number divided by infinity is always going to 0. We're going to do a couple more like this. Any questions on that one? We could do a little more algebra there to simplify. So the limit as x approaches 0 of tangent x minus x over x cubed. So if we plug in a 0, tangent of 0 is 0. Remember the hand trick, tangent square root of the top over square root of the bottom. So 0 minus 0 is just going to 0. 0 cubed is 0. So this is our indeterminate form, so we can do L'Hopital's. Derivative of tangent, secant squared. Derivative of x is 1. Derivative of x cubed is 3x squared. Okay, secant is the reciprocal of cosine. Cosine of 0 is 1, so secant would be 1. So 1 squared minus 1, and 3 times 0 squared, 0. So we have to do L'Hopital's again. So for the secant squared, you need to think of it like this. It's like the secant of x with the square on the outside. So the 2 comes down, inside stays the same, we'll subtract 1 from the power, times the derivative of the inside. What is the derivative of secant? Secant x times tangent x. Secant x tangent x. And you guys might need to refresh your trig derivatives. Minus, what's the derivative of 1? 0. Over a derivative of 3x squared? 6x. So we have the limit as x approaches 0. 2 over 6, I can reduce that to a 1/3. Secant squared x, tangent x, over 3x. Okay. Is this helpful so far? What's the top? 0 over 0 still. Okay, but if I just continue doing this derivatives, now it's going to get uglier, isn't it? Okay, so let's go back. All of our other tricks for limits still work. So I'm teaching you L'Hopital's, but that doesn't mean it's the only thing you can do. And it doesn't mean that's always the easiest thing you can do. So let's try rewriting this a little bit. I'm just going to, for a second, write a 1 over 3x out here. Secant is the same as 1 over cosine. Tangent is sine over cosine. Okay. I'm going to do a little regrouping here. I'm going to take these cosines, that's cosine cubed, I'm going to put them into my 3. And then I'm going to do sine x over x. Okay, I did that intentionally. Remember, a long time ago, but we learned a rule. The limit as x approaches 0 of sine x over x goes to what? 1. Cosine of 0 is 1. Right? So I could evaluate this. this piece goes to 1, we had a rule a long time ago. Cosine of 0 is 1, so this whole thing turns into 1/3. So just don't get stuck thinking that L'Hopital's is your only option. Okay? There are other things that we can still do. It's just been a while since we've used them. Questions there? That's good. Alright. So limit as x approaches pi from the left of sine x over 1 minus cos x. Okay, sine of pi. It's like sine of 180 degrees. What'd you say? Secant. What is the cosine of 180 degrees? Negative 1. Do I need L'Hopital's here? No. So 0 over 2, which is 0. It's not an indeterminate form. So you only use it if you need to. Questions there? I'm gonna go ahead and stop there today. I want you guys to practice this before we do more.
This is actually a serious question.
Okay.
I'm just trying to be smarty pants. Could you name us a couple of situations in which we use this rule
Well,
outside of this class?
Okay.
In another math class?
sure. Keep in mind all the applications for derivatives. You know, we've used them for maximizing and minimizing things. If you're thinking probably the most common applications. So sometimes you have uglier functions. You have to be able to do techniques to simplify them first. And so that would be if you're modeling real world situations, it's very uncommon for them to be nice, pretty functions, so the ugly stuff does pop up there. Thank you for asking a serious question.
Yep.
Appreciate it. Okay. So before we learn any of the others, I want you to practice just these types of problems. And I'm giving you quite a bit of time right now.